In this video, we're going to start Chapter 11 of the statistics textbook. So the opening section of Chapter 11 is just an introduction to the RMS error for regression. So, okay, RMS is the root mean square. We've already talked about RMS previously in the textbook. If you remember, RMS, root mean square, was the parameter that was used in the process of calculating standard deviation. So to calculate the standard deviation, you have this list of data points. Then you first determine the average. Then you make like a second column next to the main list. And that second column is the deviations of that value from the average. It's going to be some positive or negative deviation. Then you compute the RMS of that list of deviation values, and that's the standard deviation. And to compute RMS, all you're doing is you're taking the sum of the squares of all of the values, so square each value and sum them, then divide that sum of the squared value by the number of values, then take the square root, and that's RMS. Now, if you're following along in the playlist, then in the previous video, I talk about just in general what exactly RMS is, what its purpose is, and when and why do we use it. And I would recommend that you watch that video before watching this video, before going through this chapter. And the reason is because if you're like me, when I was first learning statistics, the RMS error for regression was something that it was this abstract concept, and I'd see it in Excel, right? You click to get the equation of the regression line, or the curve fit line, and then you'd show the R squared value was this RMS error for regression value. When I was first learning statistics, I would hear things like, RMS error for regression, and it would come off as this abstract concept with all kind of stuff underlying it, right? You see like R.M.s. error and regression, all these big terms, where in reality, the root mean square is just another way of kind of calculating an average magnitude of a set of data. And so if you don't have a good understanding of what RMS is, then it's easy for any time there's an application of RMS, it's easy to overthink and overcomplicate what's going on, right? Like, so we're going to be getting the RMS error for regression. And so what you can think about is that based on the previous video about RMS, when it comes to error values, like uncertainty in measurement or any kind of error values, that it's like this fluctuation above and below the actual value, right? Well, you could calculate an average error by taking the average of the absolute values of the errors, right? So you don't care if it's positive or negative, just take the absolute value, get the average. But it's probably a better idea to use RMS, because when it comes to error, if you have a error that's large in magnitude, you probably want to put a little more weight on that, right? And that's why you'll see for a lot of applications, when it comes to just quantifying the average magnitude of error, RMS is used. So it's really that simple. But you can see, if you're not familiar with exactly what RMS is, it's so easy to, r.m.s, regression, these big words, it's so easy to overcomplicate what's going on. We could have just as easily, for some like error, try and quantify the magnitude of error, just taking the absolute value, taking the average of the absolute values of the errors. It's kind of been the same idea. It's just RMS is it's a better way of doing it. So, okay, let's get into this section, and you're going to see that what we're doing here is really simple as far as the RMS error for regression. So the regression method can be used to predict Y from X. However, actual values differ from predictions. By how much? The object of this section is to measure the overall size of the differences using the RMS error. For example, take the heights and weights of the 471 men, age 18 to 24 in the Haynes 5 sample. Here are the statistics. So the average height, 70 inches. So let me bring in that chart. So there's the chart, the scatter plot, height versus weight, or weight versus height of men age 18 to 24. Average height 70 inches, average weight 180 pounds. Here's the standard deviations. Here's the correlation coefficient. To review briefly, given a man's height, his weight is predicted by the average weight for all the men with that height. Yeah, so the regression line is weight on height. So the weight is, or the height is the input. The average can be estimated by the regression method. Figure 1 shows the regression line. Person A on the diagram is about 72 inches tall. Yeah, so you've got, here's person A. So this person A and person B are arguably outliers. Those are way outside of the main cloud here. Okay, but what they're saying is that what we want to think about is what's the error of these or any data points. Well, all it's going to be is we have an input, right? And as far as we're trying to predict the output, right? And we're doing that with the regression method. We're just taking the average of all of the y values of the data points that correspond to that x value, and that average is our best guess for what the predicted value should be. Well, that's the error. It's just the vertical distance from that point to the regression line. That's it. It's that simple. It's not the RMS error. This is like the actual error. This could be a positive or negative value. It's just saying, look, you have a data point. How far is that data point from the average value of all the data points within that input value? It would be the same idea if we had weights as the input and heights as the output. You give an input, right? And now you have a predicted value that's based on the average of all of the heights that correspond to that input. That's where the regression line either goes through or is ideally supposed to go through. You try and make the regression line closely fit the point of averages as best as you can. Okay, but then from there, the error of a data point, the regression error, right? We're talking about regression error is we say it's the distance as relative to the dependent variable, the distance that the dependent variable is from the regression line. So it's going to be a straight line, either a vertical or horizontal straight line. That's going to be the error because it's just the output variable distance from the regression line. Now, but okay, we can kind of ask the question though. So, okay, are we talking about the distance of a point from the point of averages or the regression line? So let's keep reading. The regression estimate for average weight at this height is, for point A, 192 pounds. However, A's actual weight is 456 pounds. The prediction is off by 246 pounds. Okay, so what they're saying is that the error is relative to the regression line, not the point of averages, the regression line. So in the diagram, the prediction error is the vertical distance of A above the regression line. Person C on the diagram is 80.5 inches tall and weighs 183 pounds. The regression line predicts his weight as 243 pounds. So there's a prediction error of minus 60 pounds. In the diagram, this error is represented by the vertical distance of C below the regression line. So the error is the distance parallel to the variable you're trying to predict, right? You have an independent variable that you have, and then a dependent variable that you're trying to predict. So like you've got these data points. You've got some data points, and then the idea is you bring in some new data point. You know it's a certain value, one of the two values. So that's the input, and now you're trying to predict what the output is. Okay, you use regression to do this. The error in your prediction is the straight line distance parallel to the axis of the variable you're trying to predict to the regression line. So I'm just trying to give you a sense for the fact that if we could do this, an error could be a horizontal line as well. But it's going to be a vertical or horizontal line unless you have some different kind of axes, right? So it's just this vertical or horizontal straight line to the regression line. That straight line parallel to, just solely based on the output variable that you're trying to predict. Not the input variable. You're not trying to predict that. That's exactly right. You have that. Okay, so The distance of a point above or below the regression line, that's the error. This could be positive or negative. That's the error. You could think about this as the regression error, to be more specific. You could define any kind of error you want, but we're talking about the regression error here. Now, you might say, well, okay, but aren't there different regression methods? We've only learned one regression method, the standard fundamental, the regression line method, but what about some other regression method? Well, the way you can think about this is that if you, for any kind of regression method or curve fitting method, even if it's not regression, you're generating a curve, right? Whatever that curve is. And so once you have that curve, the error of a certain, the error associated with a certain data point is just that straight line distance parallel to the axis of the variable you're trying to predict to the curve, the regression curve, or just the general curve fit. That's curve fit error, regression error. Okay. Figure 2 shows the connection between prediction errors and distances from the line. So yeah, you've got there's the predicted output, there's the actual value, and then there's the error, right? So the overall size of these errors, so just like a general measure of the magnitude of the errors for the entire data set, is measured by taking their root mean square. The result is called the RMS error of the regression line. So again, you could do the same thing by just taking the average of the absolute values of the errors. But instead, we take the root mean square of all of the error values. You've got all of these. You could make another list of all of these regression error values for every single data point. And you could say, okay, just to give a sense of the magnitude of how far these points are away from the regression line, we could take the average of the absolute values, but a better way of doing that would be taking the root mean square of these error values, and that's what we do. And this is called the RMS error of the regression line. So, okay, go back to figure 1. Each of the 471 points in the scatter diagram is some vertical distance above or below the regression line, corresponding to a prediction error made by the line. The RMS error of the regression line for predicting weight from height is just, the sum of the squares of all the errors divided by the 400 number of data points, 471, take the square root. This looks painful, but the answer is about 41 pounds. Yeah, so this looks painful. They're saying this looks like it's a lot of work, but it's telling us that there's going to be there's a shortcut through this arithmetic that we'll look at in the next section. The RMS error has a graphical interpretation. A typical point in figure 1 is above or below the regression line by something like 41 pounds. Since the line is predicting weight from height, we conclude that for typical men in the study, actual weight differs from predicted weight by about 41 pounds or so. So yeah, it says the RMS error has a graphical representation. How do we interpret what RMS error is? Well, how would you interpret if we took the average of the absolute values of the errors? How would you interpret that? Oh, well, it's just kind of a measure of how, in general, what the error was, how big the error was in general. That's what this is. But it's just probably more accurate because it's giving a little more, you would think the average of the absolute value, the average of the absolute values might be a little too low, right? If there's some big errors, well, this accounts for that. RMS accounts for that. So it's just a measure of, you're saying that on average, you could say that the RMS is telling you that on average, but you probably would want to say average, right? People might get upset, but it is kind of like saying that on average, the data points relative to as far as the value you were trying to predict, the weights, right? Given input height, on average, the weights differed from, here it says different from the predicted weight. They're not differing from what you expected them to be. I mean, it is what it is. The way they are what they are. But so, I mean, it's just look, the weights are scattered around the regression line by an average of 41 pounds. And so you could word that however you want. If in general, if you tried to predict the weight of a man given his height, you're going to be off by around 41 pounds in general. I don't know if you could say it's what you expected the man to weigh. I mean, that's just inherently about the data. The RMS error is more of just telling you how accurately you can predict a man's weight given his height. It's giving you a sense of that. Yeah, so the RMS error for the regression says how far typical points are above or below the regression line. That's it. That's all it's telling you. So no, I don't. Is that what they said? This is not. It's a man's in general going to be 41 pounds away from what you would expect him to be. That's not true, because what you expect to happen is going to be based on the correlation coefficient, how scattered the data points are around the regression line. So it's really just telling you it is what it is. It's like sort of like an average amount that points are away from the regression line, above or below. But it is desirable to have a low error, though, in all circumstances, a low error in the sense that it is telling you how well you're able to predict the output given the input. It is telling you that. The RMS error is to the regression line as the standard deviation is to the average. For instance, about 68% of the points on a scatter diagram will be within one RMS error of the regression line. About 95% of them will be within two RMS errors. This rule of thumb holds for many data sets, but not all. It is illustrated in Figure 3. So yeah, this makes sense because it's very similar. This is extremely similar to the standard. This RMS error is extremely similar to the standard deviation, in that we're taking deviations from the regression line, which is like supposed to go through the points of averages, right? The regression line ideally goes through these points of averages. We're calculating these errors in the sense of their deviations from the average, then taking their RMS of all these errors. That's very similar to the standard deviation. Very similar. Not exactly the same, but very similar. Okay, now, but with that being said, they talk about how it says, for instance, about 68% of the points on a scatter diagram will be within one RMS error of the regression line, 95%, etc. The only thing I don't like about what they're saying here is that it's kind of implying that the standard deviation is only something you use with normally distributed data, or only something you can use with normally distributed data. Yeah, I mean, we did talk about how the standard deviation is best suited for normally distributed data, and sometimes it's hard to use standard deviations with non-normally distributed data. That's why percentiles are used in a lot of cases. But no, I mean, you could calculate the standard deviation with any data set you want. It doesn't matter what it is. And same here. Okay, but in this case, though, the reason why they're saying that we expect about 68% of the points in the scatter diagram to be within one RMS, etc., is because of the football-shaped cloud that we're kind of at default talking about right now. That football-shaped cloud is kind of just this normal distribution. And so with that, since it's kind of the data points are more normally distributed around the regression line, so we expect to see this 68% of the points to be within one RMS and 95% that normal distribution. But what I don't like about this paragraph is it's not like if you were looking later on at some non-linear kind of regression method and whatnot with a non-football shaped cloud that you couldn't calculate a standard deviation and you couldn't calculate an RMS. Yeah, you can. Why not? You can calculate a standard deviation with anything, any data points. You can calculate RMS with anything. Just get the deviations of the points from the regression curve, whatever, even if it's a line, whatever it is, take the RMS. But if it's not a football-shaped cloud, you're not going to see this 68% of the points. In general, you're not going to see this, right? This is for data that's normally distributed. Okay, here's the Figure 3, where it's illustrating that rule of thumb, in that you could approximate how with the football-shaped cloud that 68% of the data points are going to be within one RMS of the regression line, just a pure, well, yeah, it's a vertical distance, but then you're still parallel. It's a vertical distance here, but then going to the y-axis, you're parallel to the regression line. So 68% of the data points are going to be within this rectangle here, and then 95% within two RMSs. Okay. What about the height weight data? So the Haynes study, how does that match up with this here? The computer found that the predictions were right to within one RMS error for about 72% of the data points. So that's close to 68. And then, yeah, the predictions are right to within 2 RMS errors for 96%. So yeah, pretty good. That's going to, with football-shaped clouds, this is what you'll see. Soon we will compare the RMS error for regression to the RMS error for a baseline prediction method. The baseline method just ignores the X values and uses the average value of Y to predict Y. With this method, the predictions fall along a horizontal line through the average of Y. So yeah, we want to keep this in mind because this is going to be like a reference error that we'll use where, okay, so if we're predicting, if the dependent variable is Y, we're predicting the Y's, then we can think about another way of looking at error is just take the average value of Y, this horizontal line, and then get the distance of the data points from that line in the Y direction. And if you take the RMS of those errors, well, that's the standard deviation, right? It's just the deviation of the values from the average. Take the RMS. That's what standard deviation is. Graphically, the prediction errors for the second method are the vertical distances above and below this horizontal line, as shown by the sketch. Numerically, the errors are the deviation from the average. So the RMS error for this second baseline method is just the standard deviation in the Y. Right? That's the standard deviation is the RMS of the deviations from not the regression line average, the actual average. That's what standard deviation is. And that's why the RMS error is very similar to the standard deviation. Right? So maybe we're going to, when we in the next section, when we learn a simpler formula for calculating RMS error for regression, we might use standard deviation, right? Since they're so closely related. The standard deviation of Y says how far typical points are above or below a horizontal line through the average of Y. In other words, the standard deviation of Y is the RMS error for the baseline method, predicting Y by its average, just ignoring the X values. So yeah, again, this just really shows you how similar or how closely related the RMS error for regression is to the standard deviation. It's you have the RMS or the regression line would be something like this, right? It's just the averages that corresponding to each input. Well, with the RMS error, it's the same thing as you would do for the standard deviation, except you get the distances of the points from the regression line instead of this horizontal line that goes through the actual average of the data, the entire data, not the individual averages. Okay, let's go through these exercises real quick. Look at figure 1. So here's figure 1. Person B is what and what, while D is what and what. So the options are short, tall, skinny, chubby. So person B is tall and chubby. While D is short and skinny. Okay, look at figure 1 and say whether each statement is true or false. E is above average in weight. So E is above or below average in weight. So E is just below average. So this is false. E is above average in weight for men of his height. Absolutely. He's the leader. There's not that many data points. Yes. A regression line is fitted to a small data set. For each subject, the table shows the actual value of Y and the predicted value from the regression line. The value of X is not shown. Compute the prediction errors and the RMS error of the regression line. Okay, so we've got the actual value of Y and the predicted value of Y. That this is based on the regression line. So we need to get it's very similar to the standard deviation, but we're just going off the averages of the regression line. So we start by getting the deviation of the actual values from the regression line. So let's see. This is 7 units. The predicted value the actual value is 7 units below the predicted value. This is 1 unit above. This is 3 units above. This is 1 unit below. This is 4 units above. So there's the error, the deviation from the averages. So now we just do the RMS. So 49 plus 1 plus 9 plus 1 plus 16. So 49 plus 1 is 50 plus 9 is 59, 60. So 76 divided by 1, 2, 3, 4, 5. So, okay. Let's just do this here. So, all right. Did I get those? 1, 3, 1. Yeah, so 49 plus 1 plus 9 plus 1 plus 16 divided by 5, and then take the square root of that. 3.9. Okay, below are 3 scatter diagrams. The regression line has been drawn across each one by eye. In each case, guess whether the RMS error is 0.2, 1, or 5. So, okay. One thing we want to keep in mind here, which is kind of confusing because we didn't really have to look at this when it came to like correlation coefficients, but with the RMS error, it's going to depend on, so here we've got, look, 40, 30, 20, 10, and here we've got 4, 3, 2, 1, but it's a similar scatter, but with RMS, that's different. That's different. It's going to be, if these are on average, 2 units from the regression line, and these are on average 10, 20, whatever, that's going to be, you're going to get a bigger RMS, right? So we can think about that. This looks like it's going to be on average around 1. So this is going to be 1. This with the similar scale is just, but it's less clustered than the 1 here. So this is 0.2. And even though this is like a similar scattering about the line, it's a bigger scale. So this we'd say is 5. A regression line for predicting income has an RMS error of $2,000. It predicts someone's income as $20,000. This is likely to be right, give or take a few $100, a few $1,000, or $10,000 or $20,000. So we have a regression line for predicting income. The RMS error is $2,000. Okay, so now we get a prediction for someone's income as $20,000. So how likely is this to be correct? Well, that's exactly what the RMS measure is giving us. That's exactly what it's giving us. How off is your prediction going to? If you have an input and you're making a prediction, right? A regression prediction. So like there's an input, and now you're going to predict an output using the regression line, regression. The RMS is telling you how off on average your prediction is going to be. So we would say a few $1,000s, not hundreds, not tens of thousands, just a few thousand. An admissions officer is trying to choose between 2 methods of predicting first-year scores. One method has an RMS error of 12. The other has an RMS error of 7. All things being equal, which should you choose? 7. All things being equal, I mean, yeah, it depends on the circumstance, but all things being equal, why wouldn't you want a lower regression error, RMS error? Why not? Again, I mean, it depends on the circumstance, but like in general, why wouldn't you rather have a more accurate prediction? Okay, a regression line for predicting test scores has an RMS error of 8 points. About 68% of the time, the predictions will be right to within. So yeah, if it's this football-shaped scatter plot, then yeah, 68% of the points you could think about is going to be within 1 RMS, about 95% within 2. It's just like a standard deviation. The scatter diagram on the next page shows incomes for a sample of 168 working couples in Louisiana. Summary statistics are as follows. So let me bring in this chart. Okay, so the average husband's income is $45,000. There's the standard deviations. Average wife's income. Okay, if you predict wife's income as $28,000, ignoring husband's income, your RMS error will be the standard deviation. If you're ignoring then you're just, the best you can do is just look at it relative to the average, right? If you're predicting the wife's income, just if you're trying to predict the outcome of a single data point, the best you can do is just look at the average, is predict what the average is. If I'm going to have to, if you're going to give me something, if you're going to ask me for my best guess on what something is going to be, and all I've got is just a set of data points that corresponds to that, the best guess I can give you with no other information is the average, right? So that's why we're in this case, we think about the horizontal line that goes through the average wife income, 28,000. And so the RMS error is going to be the standard deviation of the wife's income, the 20,000. Okay, all the predictions are on one of the lines in the diagram. Which one? Yeah, the horizontal line that goes through the average wife's income.